So it's always a great pleasure to talk in Santa Cruz Galaxy Workshop. And I think my job here is every year to update with you about the progress on studying giant star-forming clumps in distant galaxies. Those eye-catching, interesting, and also important features of distant galaxies. So as an observer, I would be happy to talk about all the observations that I have done with the CANDELS team. But this year, since I'm putting in this session of simulation and deep learning, so I'm also going to talk a little bit about simulation and deep learning of clumps. And I hope we still have time for lunch after my talk. OK, so here are more examples of clumps from my 2015 paper. So we can see those clumps at the redshift 1, 2, 3. And those are massive galaxies, low-mass galaxies. You see the clumps everywhere, almost in rest frame UV, optical, and emission line images. And the stellar mass of clumps is very large, 10 to 7 or 10 to 9. And the size is a little bit uncertain, maybe a few hundred PC or 1 kPC. And definitely, they are much larger than local star-forming regions. And they are blue. They have blue UV optical color, which means they have very high specific star formation rate. And in total, they contribute 10% to 25% of star formation in their host galaxies. And many clumps are found in rotating disks based on either morphology or kinematic analysis. OK, so why do we care about clumps? Because clumps are ideal lab to test our knowledge of star formation feedback and galactic structure formation. So we want to know what's the formation mechanisms of clumps. Are they due to violent disk instability, or the gas accretion itself is clumpy, or minor merger, major merger? So that can tell us the mass assembly way at high redshift. And also, yesterday I heard about the study of globular clusters birthplace. So this is also a connection to the formation of clumps. And what's the evolution of clumps once they formed? Are they go inward? Are they going to the center? Stay long enough to be able to migrate into the galaxy center, or they are quickly disrupted in their birthplace. So that can tell us information about the bulge formation and even supermassive black hole formation, or our knowledge on feedback models, also even ISM models. I'm not going to talk each of them. Today, I'm going to focus on how to use clumps to test the feedback models. And here I'm showing you a nice plot from Shagnu 2012. So here he runs simulations on the same galaxies, one with same condition, but in one he turns on strong galactic wind, and in the other one, the galactic wind is almost zero or very weak. So if you look at the same clump, if you have a strong galactic wind or strong feedback after about 50 million years, the clump is disrupted by the feedback. But if your wind is weak, or if you don't have any wind at all, so the clump will gradually go into the center to merge with other clumps and to build up the progenitor of today's bulge. And the time scale of the inward migration depends on model, could be 200 million year or up to 500 million year, and also depends on the dynamic time scale of the galaxy. OK, so now you can feel that if we want to separate the scenario of inward migration and quick disruption, so age is the best parameter that we can use. And here is a plot showing you how we can use age to test the different feedback models. Here are two galaxies, this one from Vela and this one from Fire. Two simulated galaxies. They have a similar morphology. But if you look at the clumps detected in this one, and the age difference of the two populations of clumps is huge. So Fire galaxies, they have clump age around 10 million years, not more than 30 or 50 million years. But if you look at the clumps from Vela, the age is about 100 million years, and even 300 million years. So if we, and we know that Vela and Fire, they have different feedback models. Vela also use supernova feedback plus UV radiation pressure feedback, and the file use supernova feedback, also use UV and IR radiation pressure feedback. So if we want to test which feedback is more realistic, one way we can do is to look at the age distribution of clumps. Okay, now I'm going to the observation. So now, thanks to CANDELS, and we have optical and near-infrared images with very high resolution to resolve each clumps, and then we can study the SED and the stellar population of clumps. And here is a result from my 2018 paper, and here we show you the age of clumps as a function of their distance to the center of their host galaxies. So galaxy stellar mass increase this way, redshift increase this way, so different mass and redshift beam. So if you look at here, for galaxies at redshift below 2, so this is a 1 to 2, 1 to 2, 1 to 2, 0.5 to 1, you find this steep age gradient that clumps close to galactic centers are older and the clumps in outskirts are younger. So this is consistent with the inward migration scenario. But if you look at redshift 2, we didn't see a very clear trend. Okay, so in that way, we would say, okay, we see some very old clumps as predicted from a VELA. And this is only based on broadband SED fitting. You can argue that the SED fitting is not that good in terms of measure age of stellar population. So that's why we need to bring in other observations. So one way you can do is combine SED, broadband SED with the GRISMA from HST, and that also allows us to get a larger sample of clumps. So from GRISMA, we can get emission line maps, for example, H-alpha map, H-beta map, oxygen 2, oxygen 3 maps. So here is a recent work from Zanzello et al. So they have not only broadband images, but also GRISMA images. So they can get, I think they can get H-beta and oxygen emission images for galaxies, 53 galaxies at redshift 1.1 to 3, and this is age. This is mass of clumps. So you can see clumps, what we see from images are really a mixed bag. So you have some compact clumps, which could be in situ, formed in situ, gray points here, and you also have some extended clumps, which could be ex situ clumps, meaning minor merger or major merger, red points here. And this is the average age of in situ clumps. This is average age and the mass of ex situ clumps. Now, if you overplot the age distributions from the two simulations that I just mentioned, so this is the age distribution for file. This is the age distribution for VELA. So it looks like VELA is doing a better job to match the average age of clumps. But don't forget, we still have lots of young clumps that we observed, and somehow file matched that population. Okay, that doesn't mean that we solved the issue, because the sample is still small. We only have they only have 53 galaxies, and what we want to know is not only the age distribution, but the age as a function of distance to the galactic center. You cannot see very clear trend from their data. And if you look at my result from 2018, if you look at redshift 2, it's flat. If you look at redshift 1 to 2, it's steep. And if you look at the prediction from Mandecker et al. With the VELA simulation, it's steep increasing when you go to the inner part of galaxies. So I would say we need a larger sample to get more emission line, or to get more, to get other bands, to get a robust or more accurate measurement of age, so we can separate the different feedback models. And the power we need to separate the different feedback models is we want to know clumps whether they are short-lived with age of below 50 million years, or long-lived with age above 150 million years. And soon we will have new observations. So this is a UV observation from HST. So here, just look at this galaxy. You can see this is very interesting. look at this clump. It's almost disappeared in UV, but it's extremely strong in H-alpha. So if you think H-alpha and UV, they are basically tracing the star formation rate, but at different time scale. What does that mean? Does that mean this clump is just a newly formed clump with the age as young as 5 or 10 million years? And if you look at this clump, you can see it in UV, and you can see it in optical, but its H-alpha is just a little bit above the background. So does that mean this clump is older with enough UV light, but H-alpha contribution is small? So these are something we are going to do in the future, and we are about to get the large amount of UV data thanks to a new HST Cycle 26 program, UV CANDELS. So I have to introduce this program a little bit because they paid me. We will have 164 orbits to cover about 430 square arc minutes to get UV data, very nice UV data to 75W all the way to AB27. So AB27 means at redshift 1, you can measure star formation rate all the way down to 0.2 or even 0.1 solar mass per year. And also, we will get a very nice parallel B-band data to AB equal to 28. And here is the layout images for 4 CANDELS fields. And for CANDELS good north and good south, people already got data, deep UV data from ERS UV and HD UV in the deep region of CANDELS. So we have several scientific goals to study build-up of normal star-forming galaxies, to use UV as a calibration of star formation rate. And because we can detect the lower star formation rate, we can also study low-mass galaxies, the massive early-type galaxies, and also in the end, we are also interested in the ionizing background. So stay tuned about the progress of UV CANDELS, and if you are interested in any of these topics, so you can come to talk to me. Okay, so that's for observation, and for simulation. I'm going to quickly skip this part because I think you are more familiar with the simulation than I do. So, but I want to point out one thing that Mark also made this point. So we need direct comparison. We need mock images or synthetic images. We cannot just get a catalog from simulation and then compare to a catalog from observation, because we have to take into many difficult and observational effects. For example, pixelization and the point spread function, noise. We need not only noise, but also we need the correct pixel to pixel correlation of noise, because we are studying very faint objects here. They are quite close to the noise level, and we need realistic noise. So Kemiswaro Manta from UMKC is doing a great job to add realistic noise into simulated images. So you can talk to him about realistic noise. Okay, now I'm moving to the third part, which is deep learning. And this part is actually led by Christoph Lee. He's an undergraduate student of Joe Primark, and also Mark Herta's company is also is playing a major role in this part. So why do we need deep learning? So we really want to push the capability of deep learning to clumps, to those faint and small noise objects, to test what is the maximum power of deep learning. Deep learning is fast. We can deal with 1,000 galaxies to detect their clumps in just a few thousands. And also we can detect clumps simultaneously on multi-wavelengths, different wavelengths, different bands, and they provide a more accurate and robust measurements. And also we hope the method itself is general, and so that it's less impacted by the observational effects. It's like if your machine learns what is a cat, so it can know a cat from different images, not just knowing cat from one type of images. Okay, so this is an ongoing project, so this is more or less a progress report. Okay, deep learning to me is like this magic black box, and what we put in is images of galaxies, what we want from box is the locations of clumps, how many clumps are there, where are they. So definitely you want me to show you what's inside the box. And I'm just showing you what's inside. I'm not going to talk about what they are because it will take you lunch time. So it's called a convolutional neural network, basically the same type of network that Brent introduced in his talk. And Brent and Mark did a very nice job to introduce the background of deep learning. So I'm going to skip this part. And basically what we are doing here is we generated some simulated image as a training set. So those are not from simulation. Those are simply statistical models plus some unresolved sources. So those unresolved sources are clumps. And then we feed those raw images into the network. And in the end, it tells us what's the predicted clumps and also what's the probability of the detection, whether you should trust it or you should take it as a likely or not trust it. Okay, so here I'm showing you the completeness and the purity of our deep learning algorithm. So just look at the solid curve here, so which means for completeness, we are 90% complete, means we detected 90% of the clumps that we put into our training set. And also for purity, it's almost 90%, which means 90% of the things we detect are real clumps that we put into the training set. Okay, now let's apply our algorithm to real galaxies. So this is a real CANDELS galaxy. And here, green are clumps detected by my algorithm in 2015. And here are new clumps detected by the deep learning. So they detected also the green clumps that I detected, but the deep learning also detects some new clumps and small clumps. And if you look at this plot, so this is the detection probability as a function of magnitude of clumps. So this is my curve, 2015, and deep learning is doing a good job, better job at very faint end. The detection probability increased by almost a factor of 2. So that we can get fainter clumps, get much more comprehensive senses of the distribution of clumps. Okay, now I'm going to show you some preliminary results. First, what we want to do is we try to reproduce the clumpy fraction as a function of redshifts and the stellar mass. Clumpy fraction means if you have 100 galaxies, how many of them have at least one off-center clumps. So all the large gray points are from my 2015 paper, and the solid black lines are from the result of 5 CANDELS fields. And you probably cannot see each curve from each CANDELS field, but that doesn't matter too much here. What I want to say here is the deep learning result matches my result to some good level, and except for the most massive galaxies, my detection is a little bit, clumpy fraction is a little bit higher than deep learning clumpy fraction. But overall, the trend is the same. So clumpy fraction decrease with the stellar mass. You have more clumpy galaxies at low stellar mass than massive galaxies. And this trend is the same for almost all redshifts. Okay, now we have, remember in my 2015 paper, we only have 2 CANDELS fields. Now we have 5 CANDELS fields, so we can do some more statistics. So here are some preliminary results again. We found a weak dependence of a clumpy fraction on specific star formation rate. It's not like you have more clumps in starburst galaxies. You can have some dependence, but it's very weak. That means the clump is like a more general phenomenon in star-forming galaxies at different redshifts. And also what's interesting here is we found a very strong dependence on the size. And this is kind of opposite to what we expected. So we find the clumpy fraction is higher for smaller galaxies. And when you go to large galaxies, clumpy fraction drops quickly. So one reason could be if you if you remember from this plot, almost no dependence on star formation, specific star formation rate or star formation rate. And if you use star formation rate divided by size square, you get gas surface density. So that means clumpy fraction will increase dramatically with gas surface density. So that's the point I got from this plot. But definitely we need further investigation to rule out all the selection effects and observational effects. So okay, I think my time is running up. So I'm leaving you the takeaway message. So giant star forming clumps, they are very important and interesting. We can use them to test different feedback models. And detailed measurements of age, mass, and the star formation rate of clumps are being improved because we got new data covering wide range of wavelengths. And I want to emphasize that we need direct comparison with models and the simulations. And also deep learning is enabling very efficient studies on a very large sample. Okay, thank you.
We have time for one quick question.
So with the deep learning, I suppose you learned it using your classifications of the clumps. That's what you fed it? No.
No. We were using the training sample. So sorry. So it's like basically it's a Thursday model plus some resolved sources.
Okay.
So
okay,
this is a different. So
I thought it was really
we don't use a real galaxy as a training sample because we don't have that many classified clumpy galaxies.
Okay, let's thank Yicheng again.
Thank you.